So, okay, I
Consent
started
is
recording.
granted. Okay.
We already talked about that. Okay. Welcome to the Women Who Go Utah meetup. I am Mariah. I run this meetup as part of the Forge Foundation Meetup Circle. We're a nonprofit based out of Utah, and we run a bunch of meetups, and this is one of mine. If you want to know more about us, feel free to join the Forge Slack. I'll put a link in the chats. We've got some really awesome people in there that answer all the questions, and we have really interesting conversations all the time. 90% of the conversations are about Kubernetes, forewarning, but they're still really awesome. I guess I need to put the disclaimer that we are going to be recording this. Feel free to ask questions as needed, as you need to, or whatever. You can interrupt Julie. Just be aware that this is being recorded with the intention of going on YouTube at some future date. And if you don't want that, if you don't want to be recorded, feel free to reach out on the Slack later, and we'll be happy to answer questions then. By way of announcements, we do have a meetup next month. It'll be about Gopher.js. Troy's going to be giving
Cool.
that. Troy works at Weave with me, and he's given a whole bunch of classes on Intro to Go, so he's a really good speaker. We have officially decided to put the Go West conference as a fully remote conference. We hope to make it 100% free, and it will take place in October. So more information for that will be coming out shortly on Twitter and on the Slacks. And with that, I will turn the time over to you for your talk.
Oh, thank you. Quick before I start, you said that this was one of your meetups. What are your others?
Oh, I do the Machine Learning Utah, and then Clint does the Utah Gopher user group, and we have the Kubernetes user group, and the Utah Engineering Leadership, I think, is remote, and there's a bunch of others that have been postponed until we can get an in-person accommodations, but those are the ones that have continued via remote meetups.
Awesome. Thanks. All right. So my name is Julie Kohler. I am a software engineer at Claravine, a startup here in Utah in the marketing technology space. I am a beginner in Go. We don't use it hardly at all in our code base, but I think it's a pretty awesome language. So I have tried to push myself to learn it independently. And I'm, like I was saying a second ago, I'm still a beginner with it. So please keep that in mind today. I'm frankly humbled that anyone would want to come and listen to me talk about it. But it's a cool language, so it totally makes sense. Why it's interesting. All right, so moving on. So, why did I want to talk about the game of life? There's a bit of a backstory here. First of all, I want to make clear that when I say game of life, I don't mean the cool one that you remember from your childhood with the spinner and the little bands and the little pig people. This is something a little bit different, but it does actually kind of simulate the growth and change undergone by a type of kind of a community of a sort of a virtual community. And why I really wanted to present on it was because an experience that I had early on as I started to learn coding was I was reading something that somebody wrote, and they were like, blah, 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 Conway's Game of Life, I made one, blah, blah, blah. And they threw it out without like any explanation of what it was. And as though everybody should just like know exactly what that is. And it was just one of those things that made me go, oh, am I not in this in-group? Like that I don't know what this thing is, and apparently like everybody else does. I had kind of the same feeling about Pascal's triangle, which it turns out is actually just this, but when I first heard uh, of it, I was just kind of unsure of myself because, again, it was presented without any explanation. And what I think is that as minorities, as women coders, instead of letting those experiences that make us question if we're part of the in-group, instead of letting those throw us off balance, we should instead embrace them as an opportunity to learn more and probably learn something cool. Right? So that's kind of the spirit of my talk today. Thanks for listening to me ramble. So I've been working my way through this book, Get Programming with Go by Nathan Youngman and Roger Peppé, that I just bought because I thought it could kind of add some guidance to my experiences learning Go. And this book has been helpful in that, especially because at the end of many of the lessons, there's a hands-on part. And at the end of every few chapters, there are these capstone projects that provide a chance to really get hands-on with the concepts of the lesson. So it's not a perfect text. I have some criticisms of it, but it is kind of how I accomplished what I'm going to show you tonight, because the creating a game of life simulation was one of the capstone projects in the book. So another cool thing about the book is that the coding challenges have proposed solutions from the authors, and consulting these solutions as I go through the chapters is kind of showing me oftentimes ways that my code could be more efficient or be more idiomatic Go and read easier, or can kind of guide me when I get stuck on things. So I was just saying this is a good resource and kind of what helped me accomplish this. Okay. So a little introduction to the creator of Go, first of all, is John Conway, a British-born mathematician who unfortunately died just in April due to coronavirus. He studied at Cambridge and became a professor there, but the latter half of his career is actually spent here in the United States at Princeton. The game of life is probably what he's best known for in, if you could say, popular culture, but I guess it's like geeky culture. It's probably the discovery or invention that he's best known for, but he made a lot of other discoveries and creations, and he actually kind of became frustrated in the course of his career that life had overshadowed some of these other achievements. Sadly, like I said, he passed away just last month due to the coronavirus. It's truly a great loss. But a shout out to this cool YouTube channel called Numberphile, where they have interviews with mathematicians or have mathematicians explain something they're passionate about. And they were able to interview Conway about his game. So if you get a chance, consider checking it out. Numberphile also has like kind of a sister channel that is called Computerphile, where you get to hear awesome stuff like one of the videos is one of the first people to use the grep command because somebody had recently invented it. It's like just talk about what those types of experiences were like and some of the the internals of processors and all that cool stuff. All right. So I recommend both those. Okay. So the game of life is kind of unusual in that it is what Conway called a no-player game. It's really kind of more of a simulation or exploration of kind of what happens to, like I said, a sort of virtual community as certain rules are followed that define the game. The community is represented by a large grid made up of many squares or cells. We will start with a mixing of living and dead cells. And in this example that you see on the screen, the black cells are the living ones, and then we'll see what happens to them as we follow certain rules and the game progresses. Like you might have read in the meetup description for this event, when Conway started modeling this, he actually used a Go board because it has these squares and these black and white tiles to help us represent these binary states. Go is a Chinese strategy game, and it's not where the Go programming language derives its name. I don't think. Probably the strongest influence there is just Go's from Google, right? But I still think it's kind of cool that there's this spot where the game meets the language. All right. So moving on. Sorry. So, like I said, we're going to have this grid with these squares that represent living and dead cells, and their behavior is going to change in each generation, kind of each round of the game, based on not something about them inherently, but on the state of their neighbors. So the Game of Life was first popularized by a column by Martin Gardner in the magazine Scientific American. And here I'll quote from the article. Gardner writes, Conway's genetic laws are delightfully simple. First, note that each cell of the checkerboard has 8 neighboring cells, 4 that are adjacent orthogonally, or up, down, left, and right, and 4 that are adjacent diagonally, so these yellow ones. Like I said, each cell is alive and dead, and each step of the game, we're going to look at these 8 neighbors and follow these rules to decide what happens next to the cell. Any cell with fewer than 2 neighbors dies, as though through isolation. Right? The second rule is that a living cell with 2 to 3 neighbors will live on to the next generation, thriving through having a community almost. Rule number 3 is that a living cell with greater than 3 neighbors dies, as if by overpopulation. And number 4 is that a dead cell with exactly 3 neighbors becomes a living cell, or a birth occurs. Cell is born. So, and it's important to note that all of the births and the deaths happen simultaneously. So you decide what the state should be based on the position of, or the situation of the board at one moment, and then in the next, all of that is calculated simultaneously. It's not like the individual changes affect one another one at a time. The entire board changes in each generation. Okay, hopefully that's clear. I think it's kind of simple when you start to see it in action, but I realize that some of this might sound a little abstract to talk about it. Okay, so let's look at these different cells and decide what is supposed to happen to them in the next phase. So what about this green cell? Any thoughts? I can't hear anybody if anyone is answering.
Nobody wants their voice to be recorded.
Oh, okay. That's totally fine. That's okay. So give you a second to think about it. And it is that it is going to die because it has fewer than 2 neighbors, right? So it's almost too lonely. Okay, so let's look at this red one. Think about what will happen with it for a second here. Based on these rules. Okay, so it should be born because it has exactly 3 neighbors. This one, and down here in the corner. Okay, so as we look at the blue cell, it is going to live on because it has 2 neighbors, which is enough. And as we look at the yellow cell, you could probably infer this. It's the last one. It's going to die as though through overpopulation. Too many neighbors. Okay. So what happens as you start to morph the board like this. Oh, like this. You can see these are all of our changes tallied. Okay. Or represented all together. So what happens as you do this is that patterns emerge. Conway and others have gone on to name some of the phenomena of these recurrent patterns that they have observed, including blinkers, gliders, spaceships, beehives, puffer trains, Methuselahs. All of these are different shapes or configurations of either configurations of living and dead cells or patterns. All of these have been documented, and there's this cool Game of Life wiki that you can visit, and they actually have like pages for the individual configurations or patterns, and they will like say, oh, this happens in this generation when you start with this pattern and layout, and I don't know. It's super dirty, but it's kind of cool to see how many there are. So again, quoting Martin Gardner, he observed, most starting patterns either reach stable figures, Conway calls these still lifes that cannot change, or patterns that oscillate forever. Patterns with no initial symmetry tend to become symmetrical. Once this happens, the symmetry cannot be lost, although it may increase in richness. So what's kind of cool about the Game of Life is it's this deceptively simple thing. Like you think, I don't know, it just kind of sounds like shapes changing colors, right? But and not even colors, like it's just black and white binary states. But what you see over time is the emergence of really fascinating things. So let's talk about how I went about coding this in Go. I opted to have my to have all of my code in copied from VS Code and then formatted and put in here. So you're not going to see me open my editor. I'm just going to talk about what's on the slide. So I hope it's still an understandable way to see what's going on, and I hope it's a little bit easier to see across the Zoom here. Okay. So first thing to do with this problem about how do we code out this thing? How do we represent this? We need to turn it into a series of steps, and I totally appreciate Youngman and Peppé's help in this, because one of the good things about it is they broke it down so that you could kind of say, oh yeah, I'll probably need a method to do this and one to do this, and kind of guided that discovery. Anyway, but this should be a familiar process, because this is what we have to do anytime we have a coding problem, is do this, break it down, think about what needs to happen. So as we do that for this problem, we see that we need to make a game board, populate part of it at random, right? Seed it with a few living squares so that we can observe change. We need a way to determine whether a cell is alive or dead. We need a way to count the number of live neighbors, since the behavior of a cell will depend on, again, the situation of its neighbors. We also need to determine whether a cell should be alive or dead in the next generation based on that count. And then ideally we have a way of also changing the state of the cell. And because it's cool to see this represented visually, we're probably also going to need a method to show it off. Okay. So getting started. So as we hear the term living and dead, this should be a kind of a familiar concept, because it's essentially a binary state, like I mentioned before. And, you know, as computer programmers, binary states are kind of our thing. It's sort of the what's behind the scenes on all this. So because of the power of Boolean algebra, so we should hear this and think, this would be well represented by a Boolean. All right. Then we have a universe, or a world, or our community, neighborhood, whatever we want to call it, that is going to be a two-dimensional field of cells, right? A grid. And a good way of creating this is to use a slice of slices. And why it makes a good representation of this board is because, here, let me get our illustration on the page. Okay, so we have an outer slice, and then we have things inside of it, or more slices nested inside of it, and those nested ones represent our individual rows, and then they all have the same number of values inside of them, and they line up, and those essentially represent our columns. Right, so that's how we get our lattice pattern here, our cross, our axis and game board. Okay, sorry, so we start with the slice of slices, and then just to, once we have allocated the space, we're going to begin with all dead cells. We're going to fill it with all falses, and then in another method, come through and seed it. All right, so we begin with all dead cells, and a lot of, I wasn't sure how familiar everybody would be with slices and some of these things, and how to access members of them. So I just wanted to highlight that this center false here, if we wanted to access it, we would use first 1, because it is in the first row, 0, not the 0th, but first. And then it is in the third column, again, 0, 1, 2, 0 indexed. Okay, so I think everybody here probably knows how to access members of slices or arrays, but I wanted to be prepared for kind of a mixed audience. Okay, so we're gonna need a method that is like our world maker. Excuse me. We're going to use a function to create new universes. And since we want every single game board that we create in running the game to have the exact same size, we can save these as constants. So as we here get into our code, the size, excuse me. So now that we've defined our universe type, the first thing we are going to do is build a universe factory with it. We could call this function and it will return a new universe to us. We could have this function take arguments and return universes of various sizes, but like I said, since we want them all to be the same, we save them as constants. Youngman and Peppé opted to call these values height and width, but describing them in terms of rows and columns helped me conceptualize the game board better, so that's what I did here. So first, we're going to use the make command to pre-allocate a universe called U, and we're going to set the length of its outer slice equal to the number of rows that we want. Then we are going to loop through those rows here and make each of them a slice full of Booleans. And these will default to the 0 value of false. And these internal slices will have a length of total columns, which in this case is 5. And something that this taught me here is I was confused at first that we were calling make on universe, but we're able to do that because its underlying type is a slice. At first I was like, oh, that feels weird, like it's the wrong type, but that was why that works. Okay, so let's move on. And feel free to stop me if you have questions. I'm nervous, but I will try to answer them. Okay. So, and at this point I was like, cool, I've created my board, but I want to see that it actually got there, that it actually was made. And so we can actually print out the situation of our board by creating a show method. So this is how I went about creating a show method. I started with an empty string and then added to the string. But the authors opted to define a string method on universe and create a slice of bytes, then append that to the, like I'm doing here, but to the buffer, and then return a stringified version of the buffer. Eventually, we're going to use spaces here for the empty parts of our grid, but it's easier initially to know that you have what your configuration is if you use dashes and asterisks. So asterisks, if the value in the cell is true, and minuses if the value in the cell is false. Add a new line so that we can see the board separated over time, and then we're going to print it out. Initially, you don't want to clear the screen, I found, as you go through and you print this, because you could print and then kind of wipe, print and wipe. But it's much easier to track the changes if you just initially have it print with new lines. So yeah, this clear the screen command is OS dependent, and you might need a different character to do it. But anyway, moving on. Let's see. So now that we have our game board, we're going to plant the seed essentially by seeding the board with living cells. And to start our community, we want about 25% of the cells to be living. And when I first did this is how I went about it. You can see I loop through all of the cells and then create a random integer in each one. And then I'm like, okay, it's 1 to 4. If it's 1, I'll just set those ones to true. But consulting the solutions provided by the authors, I found this more efficient way where instead you you continue your iteration until you've reached something that is the equivalent of 1/4 of the board. And then you call set on a random integer each of those times. So instead of going through all the squares, you only have to go through 1/4 of the squares. So that's clear win. And this set function, it's another method on universe, and it just takes in a column and row and a Boolean, and then sets the value at that row and column equals that Boolean. Okay. So moving on here. Another one of the things that we said that we needed was a way to tell if a cell is dead or alive. And to do this, we're going to need to look it up in the universe. And this process of looking up was the source of some bugs and confusion for me initially, because I was thinking, okay, these are going to be X, Y coordinates, right? And you're used to going X over first and then Y up or down. But in fact, if you want to do that with your slices, first you need to get into the row, which is the interior slice, and then you can start going across its elements, which represent the columns. And so that threw me off. I kept getting configurations that shouldn't have been possible according to the rules. I was like, what is going on here? And it's because I had done U column row a bunch of times, thinking in the mode of XY. Anyway, I hope this isn't just tedium, you guys. I hope this is actually interesting. Okay, so we come into this wrinkle when we see the when we get to the edges of the board, right? And so we're going to use the modulus operator to kind of get us out of the problem. So if we're passed into our alive function something like the 100th column or the 150th column, and we only have a total possible rows of 100, what we're going to do is use the modulus operator, and we'll sum what we've been given with the total, and then take that sum and use modulo 100, or the total limit to get the remainder. As a tip, I see this situation a lot on Code Wars because a lot of those are like Caesar ciphers. And so this is useful for that because eventually your Caesar cipher, you get towards the end of the alphabet and you need to go back around to the other side. Anyway, just a side note there. Okay, so then we go through these neighbors and we loop around and we're checking if the neighbors are alive. And it doesn't matter if if we go off of the board. We don't have to accommodate or calculate that in here because our alive function is already taking care of the overflow and the wrapping for us. So how I did this originally when I very first went through it, I didn't even do 4. I just did the column -1, or the row -1 and the column -1, and then all of the different versions, like the row -1 and the column even, so that you get around the borders here. So, but then I eventually turned it into a couple of for loops where we're going through the rows, then we're going through the columns, and the only time we don't count it if it's alive is if we're in the center of the spot. Okay, moving on. So, a cell. Okay. So then once we have this way of determining whether things or what our neighbors are and if they're dead and alive, we need to figure out what does that mean for the cell in the center, for that red cell there. And so when I originally did this, I had like an if the cell is alive, else, and then I had a switch statement for the neighbors, which is so much more than you need to calculate this. Even as I wrote it, I was like, oh, this is kind of bad. But consulting the solution showed this much nicer way of there's really only kind of 2 conditions at play here. Does it have 3 neighbors? Because living cells and dead cells both will be alive with 3 neighbors. And then otherwise, does it have 2? And then you can check if it's alive. All right. So, I mean, it's 3 conditions, but broken down into kind of 2 parts here. Very, very nice. Okay. So, with every step that we take, we're going to take 2 universes and take the situation of universe A and then transfer it to universe B for the next step, and the next state. And then we'll take universe B and set it to the condition or the state of universe A, so that we make sure that we have these independent things where our changes don't affect one another, right? So with every step that we're taking, or with each generation, what we're going to do is loop through all the rows and columns and then set in B whatever the value that next tells us it should be from universe A. Okay. And I kind of forgot to mention that a lot of the virtue of having a universe type is that we can then have all of these methods on that type. So here you see we're calling the set method on B and the next method is on A. So that's one of the benefits of types, right, in Go. Okay. So then let's look at our main here. And so those of you with more experience in Go can tell me if this is the spot that I want to seed random to make things work. I wasn't sure if this was the best place or what, but I would appreciate input on that one. Anyway, so as we begin this, we first create our two universes. We seed the first one. We decide the number of generations that we want. In this case, I'm using 5 generations. We take the step. We show what the situation in A is. And then we flip them around. And you can use the sleep function so that you can kind of watch these changes over time. Because this will, force the program to pause for a second or however long you set it for. So let's watch this in action. Here's the cool part. And at first I'm going to show you how this looks with like a very small board, just 5 rows and 10 columns. And it's going to show you the all of the iterations, because this is how I began, so that I could kind of see, am I actually creating valid configurations here? Does the mesh check out, basically? Okay, so let's watch this run. The next one will be different than this last one because of our randomness. Okay, cool. So I realized that in this, they kind of just look like dots on the page, but we've got the dots on the page to change according to rules, and it's kind of awesome. And like I said, cool things can happen as you have lots of generations and lots of space. So here is another example I prepared with a much bigger board and 1,000 generations. Time is sped up a lot in this one. Okay, here we go.
Those dots kind of look like weird animals sometimes that are just circles.
I feel like we stopped with Yoshi. Doesn't it look a little bit like that?
I can see a Yoshi.
Yeah. Okay. Totally screenshotting this. Cool. So you can see, like, even right there, it's like it's super nerdy, but like as you get into this and you watch these patterns change, it's kind of exciting and fun. In fact, going back to our presentation, I wanted to show part of this YouTube video. Somebody called it the best of Conway's Game of Life, and some really cool configurations I've seen in it. It feels like you're at the microscopic level down here. It's wild. Those are gliders, I think. More gliders, and looks like there's a tiny war happening down in the beacon side. Okay, well, those are a couple of the coolest ones in that video. They go through a few more. It's just, you can really get into like how fun it is to see these things happen. And I think that has a lot to do with the people's continuing fascination with the game of life, because it's this thing that feels organic and spontaneous, even though you have these rigid rules, and even though it's like it's just a grid. Like, how much less organic could it be? It's like a grid on a computer. It feels so separated, but it kind of looks like it's representing the real world. It's just super fun. Martin Gardner said, "You will find the population constantly undergoing unusual, sometimes beautiful, and always unexpected change." And it reminds me of William Blake's Auguries of Innocence, which starts to see the world in a grain of sand and a heaven in a wildflower. hold infinity in the palm of your hand and eternity in an hour. And I think these little dots changing kind of are like our grain of sand on the world that is our game board here. To wax a little poetical about it. So now that you're familiar with the concept of these 2D slices, there's a lot of games that you could build, like tic-tac-toe or Othello or Tetris or Mancala. There's a lot of these things that they have these game boards that are well represented by our 2D slices. If I personally continue working on this, I'll probably do it in the form of tests, tests that check, hey, did you have this configuration after this move? Just to kind of push my program a little bit farther. So some sources and further reading that you can consult if you want to know more. Martin Gardner's column in the Scientific American, conwaylife.com, which has the link to the Conway wiki, where they track all these different forums. Their forums are happening. Like I checked them just today, and like there have been like a bunch of responses in the past few hours. There's Wikipedia's articles on the Game of Life and on Conway. Sadly, recently obituaries were printed of Conway in the Guardian and the New York Times, and they provide this really interesting explanation of his life. He pushed himself to be an extrovert, so he was kind of this charismatic, outgoing mathematician, kind of an interesting mix that way. And then, of course, the book Programming with Go that helped me accomplish this. Okay. All right, does anybody have any questions or anything?
I'll go ahead and stop the recording.
Okay.
Thank you so much.